right, so friction. So again, theoretically, this is something you guys learned last year. So, okay, so I think you guys all know this. Remember that friction is anytime you have two objects that are in contact. All right, friction is going to be the force that resists the two objects sort of sliding against each other. Okay, friction will always be parallel to the surface. Right, normal force is always perpendicular. Friction is always parallel to the surface. All right, and it's always going to act in a direction that is either, if the object is moving, it acts in the opposite direction from the direction that it's moving in. All right, if it's not moving, but something is sort of trying to make it move, then it'll act in the opposite direction of the attempted slide. Is probably the easiest way to say that. Okay. So there are two types of friction. All right. Static friction is friction that works against the attempted motion. It occurs before the object has started sliding. Okay? So if I go over here and try to slide my desk, static friction is preventing it from moving. Okay? Because I'm not exerting enough force to overcome that static friction. You okay, Jack? You're being attacked. I know. It's an infestation. Okay. So it seems to me that determining the direction on static friction is kind of the hardest one. Determining the direction on kinetic friction is a little bit easier. All right, so I guess I jumped ahead a little bit. So what is kinetic friction? So kinetic friction is friction that occurs after the object has already begun sliding. All right, so if I take this chair here, okay, so right now, static friction, right? If I push harder, still static friction. Eventually I can overcome that static friction. Now it's sliding. So while it was in motion there, that was kinetic friction working against this motion. All right? There's a common misconception. A lot of times people think that the kinetic friction acts opposite some sort of force. That's not the case. After I let go of the chair, the only force affecting its motion was friction, right? It's moving this way, friction's that way. Okay? All right, so that's kinetic friction. It works against the motion of an object that's already sliding across the surface. Cool? Yep. Questions about any of that? Cool. All right, so static friction. Here's a whole bunch of stuff that you need to know about static friction. So, for whatever reason, whenever I save these files, it doesn't save the formatting. So the formatting on your paper is going to look nicer than what it looks like up here. I guess this page is fine, but the next page is going to be a little messed up. All right, so anyway, static friction. Here's what you need to know. First of all, and I think this is all stuff I've said, but let me just reiterate. All right, so first of all, static friction only occurs if the object is not sliding yet, but the object would slide if there wasn't any static friction. All right? What's the force of static friction on this chair right now?
None.
0, right? Sometimes people go, oh, it's not sliding, there's static friction on it. But there's nothing sort of trying to make it move, right? The only way that static friction is there is if there's some sort of force to resist, some sort of an attempted motion to resist. Follow? Yeah.
So if the Earth is actually rotating, would there actually be static friction going in the other way of the Earth? It's accelerating.
Yes, I guess technically there would be. Yes.
Wait, what about like?
So minimally.
Why wouldn't it be easier?
Because if there was no friction, I guess the Earth would just spin underneath it, right?
Yeah. So then why isn't it easier to push the chair one way than like
Because
the other way?
it's insignificant. The force of gravity is yeah. All right. Are we good? All right. All right. So here's the next thing. Static friction acts in the opposite direction that the object would slide if there wasn't friction. Okay. So, but you got to be careful because, well, so first of all, it's parallel to the surface. All right. So, and then there's two examples here. So, a second ago, I was trying to push the desk, right? So the attempted motion is that way, right? And so static friction acts in the opposite direction, right? Okay. There doesn't necessarily have to be sort of a force trying to make it move, okay? When you turn a corner in a car, that's static friction that allows you to turn that corner. Okay? The idea is, here's your car, top view. Here's the wheels. right? And you're going around a corner, right? The idea is if there wasn't friction, your car would go in a straight line, right? Okay, and so static friction grips the tires, prevents it from sliding, and pushes the car inwards with some amount of static friction force. Okay, so please don't think that static friction has to be resisting some other force, because that's not always the case. Okay? Same thing when you speed up in a car. When you walk, static friction just pushed me forward, right? Because my feet didn't slip across the floor. Follow? All right, so the idea is when I push my foot backwards, I'm sort of trying to slide it backwards, friction resists that, and then the reaction is that I get pushed forward. All right? Okay, cool, we talked about the car. All right, the next thing to know about static friction is this. I always describe it as static friction is lazy. All right, so it doesn't always sort of exert as much force as it can. Okay, it just exerts as much force as it needs to. Okay, so as long as it can prevent the sliding, it'll do that by exerting as little force as possible. All right, eventually there becomes a point when it can't exert that force, and that's when it starts to slip. Okay, so that brings us to, oh no, sorry, equation must be on the next page. All right, again, my formatting got messed up. I didn't have time to fix it, so it looks nicer on your notes than it does on my screen, and I apologize. All right, so anytime two objects are rubbing together, there's a maximum amount of force that static friction can exert. Okay, we're going to denote that as force of friction static max. All right, I think the book just uses FS max. Again, I'm really religious about putting a capital F in front because it emphasizes this thing we're talking about as a force. Okay, I found that to be less confusing teaching this stuff in the past. Okay, so anyway, so there's, for any given sort of situation, assuming that your forces aren't changing, there is a maximum amount of force that friction can exert, all right? And that force varies depending on two things. Depends on the two surfaces that are rubbing together, okay? The two surfaces that are rubbing together determine what's called a coefficient of friction, coefficient of static friction. Right? And the symbol for it is the Greek letter mu, and then a lowercase letter s for static. All right? And we'll talk about where that comes from in a minute. The important thing to know now is that it's a ratio. It doesn't have any units. Okay? They're not exact. All right? If I give you the coefficient of friction, it's an experimentally determined number. All right? They're not exact. Okay? But here's the deal with it. In general, the smoother the two surfaces are, the lower your coefficient of friction is going to be, right? And sort of the rougher the contact between the two surfaces, the higher the coefficient is, all right? In general, coefficients are usually between 0 and 1. I meant to look it up, and I apologize for not doing so. Occasionally, you get a coefficient of friction that's higher than 1, but it's very, very rare. And I meant to look up the example, and I forgot to, so I'll have that for you tomorrow. So here's a few examples, though. Teflon that they use, to make your pancakes not stick to the griddle. If you have two surfaces that are Teflon coated, the coefficient of static friction is 0.04. The ice cube skating across an ice skating rink. Let me finish, and then I'll get you. Coefficient there is 0.1. So those are both very smooth, relatively low coefficients of friction, right? Tires are made out of rubber, right? The intent is they increase traction. Okay, so on wet road, fairly successful. On dry road, very successful. Okay, so the higher your coefficient of friction is, sort of the more grip there is. Okay, and that indirectly is going to help. It's going to be one of the things that determines how much force of friction there is. Right. So that number here, you guys, it's not the force of friction. It's just a ratio. All right, and I'll talk about sort of what it means in a minute. David, and then Carson, and then there was another thing up here somewhere.
But it seems like that's supposed to be more slide.
Surfaces which are smoother or... Oh, yeah, totally. Yeah, 100%. Thank you. I apologize. Yeah, totally more slide.
I was just going to ask if there's coefficients for those, like, the ice on ice and that sort of thing. Does it include, like, adding some more? Like, you know how, like, tires have, like, patterns versus just a flat material?
I gotcha. No, I know what you're saying. I'm trying to think about how I want to answer that. I mean, again, these numbers are all experimentally determined. You know what I mean?
Yeah.
So, one tire on dry road is going to have a different coefficient of friction than another.
Right.
And yeah, certainly the tread would be a factor. Supposedly, the surface area doesn't matter, which is always surprising to me. I think it's just because as your surface area increases, the pressure decreases, so there's sort of less swoosh between the two surfaces, So that would lead me to think that if the surface you were driving on was very, very rigid, the tread wouldn't matter. But if it's something that's going to give a little bit, then the tread would matter, right? Because then you're going to sort of be digging into that material, right? So I would guess that, like, if you're driving on cement, if you're driving on, steel, thank you, like a steel bridge or something, tread's not going to be anything.
Right.
But on snow or gravel, or then it would. Yeah. Other questions? Good? Okay, cool. All right, so that's one of the two things that's going to determine sort of that maximum force of static friction. It's that coefficient of friction, determined by how smooth the two surfaces are. All right, the second thing that matters is how tightly they're being pressed together, right? The normal force, okay? The more tightly the two objects are being pressed together, the more friction there is. All right, and here's a real simple example of that. Check this out. Like, if you put your hands together and rub them together, they'll get warm, right? So if you do this for a minute, just lightly press them together, they'll get warm, right? Okay, if you go faster, they get warmer. But the best way to make them get warm is to press tighter. Put your hands together tight and do it. They get hot really quick, right? Okay, that's because there's more friction, because you're increasing the normal force between your hands by just pressing tighter. Okay? That's why a lot of times, so pushing it, like if you've got a car parked in the driveway, and it's like, we need to slide this thing, right? So that's hard for two reasons. One of the reasons is cars are heavy, so it's got a lot of mass. It's got a lot of inertia resisting the motion of you pushing it, right? The attempted motion, right? But the other thing is because cars are heavy, there's a lot of normal force between the tires and the ground, right? Okay? And so ultimately, that's what makes it hard to move the car, right? If it wasn't as heavy, then it would be easier to slide, because you'd have less normal force, and therefore less friction. All right, good? Everybody happy?
Yeah.
Cool. Okay, so here is the equation for static friction. So the idea is, for a given object, the force that static friction is actually exerting is always going to be less than or equal to the amount of force that static friction can exert, right? This is like how much money static friction has in its wallet. This is how much it's going to spend, right? It can't spend more than what's in the wallet, right? This is like the maximum amount that it's got. This is what it's using, right? So this is force static friction can exert. Okay? So how do you figure out how much force static friction can exert? Well, it turns out you just multiply the coefficient of static friction by the normal force. Okay, so it's directly proportional to both of those numbers. Okay? More normal force means more static friction, maximum. And, rougher surfaces means more friction that we can have. Yes, Francis.
So the mu times normal force is equal to the maximum?
That's correct.
So not
Yeah, and that's a really, really important distinction. All right, so usually what will happen, you guys, in terms of here's a problem-solving strategy. Usually what will happen is, if you're given the coefficient of friction, then probably your first task is going to be, all right, well, let's figure out what the normal force is, and then use that to figure out how much force static friction can exert. Okay? And then you compare that to the force needed to prevent the motion. right? And we'll see that through some examples here, but that's sort of where we're headed. All right, are we good? Okay, cool. So, this is a complicated equation. It's an equation and inequality. Do we understand what the difference between this and that is? Okay. All right, so let's do a quick example. Okay, so we got a 20-kilogram box sitting on a floor. We're given the coefficient of static friction between the floor and the box, it's 0.65. And we're going to make a free body diagram and describe what the box will do if Roy pushes the box horizontally with a force of, and then there's 3 different forces here. Okay. So let's take a second to do this. So start by drawing the box on the floor. We know that the mass is 20 kilograms. All right. Again, remember, you always want to start by putting in your force of gravity and your mass. So my force of gravity here is just going to be 20 times 9.8, so you get negative 196 newtons. Because there are no other vertical forces, I can safely assume that the net force in the y direction is going to be 0. And therefore, my normal force must also be 196 newtons. Let's see, any given forces. We know that Roy is pushing with 80 newtons. So here's our force for Roy. 80 newtons. Pretty good up to there. All right. So now to decide if this thing is going to move or not, we got to start by finding our maximum force of static friction. So let's find our force of static friction max. Well, that's equal to the coefficient of static friction times the normal force. So my coefficient was 0.65. 0.65. My normal force we just found, that's 196 newtons. Multiply those, and you've got, let's see my notes here. 127.4. So what this tells us, this is kind of telling us, like I said before, this is like how much money static friction has in its wallet, right? And it wants to spend as little of it as possible to prevent the object from moving. So, Roy's got 80 newtons. Can he beat static friction?
Nope.
No. So static friction is going to prevent the motion. Force of friction static. How much? Just 80. That's what I mean when I say static friction is lazy. It's not going to use the full 127. Because think about what happened if it did. It would accelerate this way, right? That'd be like Roy trying to push the desk, and then the desk going like flying back at it, right? Okay, that doesn't make sense. This 80 newtons isn't enough to move it. Okay, so 80 newtons is not enough. So that means my net force in the x direction has got to be 0 also. So my force of static friction is going to be negative 80 newtons, and there's your drawing. You're done. Good or no? All right. I don't know if I need to go through B. What would I change for part B? For part B, Roy's force is now 100 newtons. Is that enough to get it moving? No. So friction is going to exert negative 100 newtons, right? And then everything else is the same. Follow? All right. Now, let's talk about C. What's going to happen in C? It's going to move, right? Because friction can't exert 130 newtons to prevent the motion. Sorry? Right. So yeah, right. We need an extra, or we have an extra 2.6 newtons, exactly. Okay. So that means it's going to slide. All right. So we can't solve part C yet. All that we can do safely at this point is say that thing's going to move. All right. Beyond that, we don't know. So C box will move because 130 newtons is bigger than my force of static friction max. It's bigger than the 127. So since it's moving, what do you think we're going to need to do?
Kinetic friction.
Use the kinetic friction, right? So in a minute, we're going to come back, we're going to revisit this example, and I'm going to give you a coefficient of kinetic friction, and then we'll solve the rest of it, okay? But I want to do one other quick thing with static friction first. Yeah, Francis.
For C, is there still a force of static friction of like 127.4? It's just not enough.
It's there for like a fraction of a second. But as soon as it starts moving, it sort of automatically switches over to kinetic. Okay? It's not instantaneous, but it's so close to instantaneous that it's treated that way. Does that make sense? Yes. All right. Are we good? Yeah.
So if you were to exert 127.4 newtons, it would not move. But then if you were to exert
Great question. Great question.
5,
So again, remember, you guys, these coefficients of static friction are experimentally determined. So because of that, this number is not exact. It's ish. You know what I mean? So sometimes people will say, you know, what's the minimum force needed to get it moving? And in this example, we would say 127.4.
that would get it moving.
It's a gray area, right? So what do you need? Well, 127.400000001. You know what I mean? So people sort of don't make that distinction. It's sort of understood that that's the breaking point.
Okay.
So sometimes that'll be discussed as, well, this is the most force friction can exert. Other times it'll be discussed as, this is the force needed to get it moving.
So the question, how much force required to get it moving and how much force to keep it still is like the same answer.
What's the most force you
What's the
could
most?
have and have it stay still? Yeah, it's got the same answer.
Okay.
Kind of like 100 degrees is, you know, both
Yeah.
water and steam, right? So the breaking point, right?
Okay.
Cool? I shouldn't have pulled out chemistry because I haven't done chemistry in a good years, so I hope I didn't just. All right, are we good?
But that's
Okay, cool. All right, so sometimes we got to go the other way. And this is a perfect example of what Alex was just asking. This question is a really, really good one. So it says a 50-kilogram box sits on a floor. So draw it. 50 kilograms. Right away, put in your force of gravity. There's no other vertical forces on it, so again, we automatically know that our normal force is going to be positive 490. And it says Roy pushes the box and discovers he needs a force of, and then I put it in parentheses. But like when you're doing problems in your book, it won't say this. It'll just, Roy discovers he needs a force of 300 newtons to get it moving. Right? So indirectly, that's a way of telling you the static friction max, exactly, right? Because if he exerts 299.9999999, then it doesn't move, 300 doesn't. Follow? So, and we're trying to find the coefficient of static friction, right? Well, so that means this is that over that, right? Our maximum over our normal force. Just algebraifying that. There you go. Okay. That's pretty good? All right, so just plug in your numbers. Your maximum friction is 300 newtons. Your normal force is 490. So divide it and you get 0.61. Notice units. All right, so a while ago when I first started talking about this idea of coefficient of friction, and I said it's experimentally determined, this is exactly what they do. Somewhere in a lab at MIT or wherever, there are dudes sitting around figuring out how much force it takes to get object A sliding across surface B, finding the minimum force, and then calculating the coefficient of friction. Cool?
Yeah.
All right. Any problems with what we just did there? Okay. Excuse me. All right, so kinetic friction. what you need to know is very similar. The biggest difference is this. Well, two big differences. One is the definition, which is that your kinetic friction only applies once the object is actually sliding. Okay? All right. The other difference is this. Once it starts sliding, the force of kinetic friction is constant. So there's no sort of maximum value of kinetic friction. Once it's moving, there's a force of kinetic friction, and that's it. And the only way that would change is if either your coefficient changed or your normal force changed. Okay? So, but anyway, let's run through the list here. So what do we need to know? It only occurs if the object is sliding. We said that. So if you've got a box sliding across a table, kinetic friction is going to work against it. Now, be careful. Sliding doesn't equal moving. Always. They're always going to be moving relative to each other, but like when you spin your tires in your car, like you're on an icy road and your tires are spinning, the car's not moving, but there's kinetic friction occurring between the tires and the ice, right? Make sense?
Yeah.
Okay. All right. No matter what, this is the biggest thing that messes people up. No matter what other forces are acting on your object, kinetic friction always acts in the opposite direction that the object is sliding. Okay? Here's a really dumb, simple example that will hopefully help you visualize that a little bit better. All right? So, check it out. Here is a giant monster which is attacking Metropolis. It's got big claws. Alright, so there's our giant monster, right? And this monster hates babies.
Wow.
Holy cow, look out! Here's a baby. Alright? That's a baby, he's just hanging out, right? Okay? And the monster pushes a school bus on its side across the ground at the baby. Oh no, look out, baby! Alright? So, if nobody touches the school bus, presumably there's friction trying to stop it, right?
Yeah.
So here's my force of kinetic friction, right? Okay? Hopefully that's enough, but maybe not. Superman comes along. It's got a little curl there. Cape. Which way is Superman pushing? Same way as friction, right? Friction, even though Superman is pushing left, friction is also to the left. Because friction doesn't care what Superman is doing. Friction just doesn't want the thing sliding this way. Right? So in that example, you've got two forces both working towards slowing the object down. That make sense? Right. I just went through this stuff with my honors kids, and they kept wanting, even though it was moving that way, they kept putting their force of kinetic friction in the opposite direction from the applied force, not the opposite direction from the motion. Okay. Yeah, House.
So this is saying we did stop the bus, then the friction would be in the switch direction.
That's correct. Yep. Yeah, so once it stops, then what happens is, all right, so now it's stopped, it's not moving. Then what happens is static friction is going to try to prevent the motion. Superman's pretty strong, so it's probably not going to work. So then, yes, you're right, and then your kinetic friction would go the other way. That's exactly correct. Okay? All right, there was another hand up somewhere, I thought.
Let me think about it. I'll come back.
Okay. All right. Cool? All right. So, okay, so, this is basically the same slide you just had a minute ago for static friction, right? Again, my formatting got a little mixed up. All right, so, if two objects are sliding across each other, the amount of force kinetic friction can exert depends on the two surfaces. So again, you get a coefficient of kinetic friction. Okay. The big thing to notice here is, in general, this should be more again. I can't believe nobody caught that in my honors classes. We have the same. So what do you notice about these coefficients, guys? They're the same surfaces that we had on the other slide. They're smaller. All right. In general, the force of and the coefficient of kinetic friction is less than static. That's why if you're driving, once you start sliding, you keep sliding, right? Okay? Yeah.
So you're in a car, you've got a stop sign up ahead, or you got a red light up ahead. You've got 3 options. Brake so that your tires don't move and they just slide across your static friction.
A lot of variables here. Which one do you do? Is that where this is headed?
Brake enough so that your tires glitch out, or you brake to the fact that they're still rolling, so they don't have any like block. Yeah, and then option 3 is you brake so hard that you have a skid on the road of the rubber bonds braking.
How's that different from?
I don't know. Is there a difference? Which
I
one?
didn't understand the difference between 1 and 2. There's a lot of variables here. There's no one answer to that. It depends on the surfaces. It depends on how fast you're going. But yes, pump your brakes because the force of friction between the tires and the calipers is greater than the force of friction between the road and the tires. Well, right, yes. And if you have analog brakes, they do that for you. All right. Too many variables for me to give you a simple answer. There's a question in the book that I didn't assign that is about that, about whether you're like driving towards a wall, are you better to jam on the brakes or turn? I think I didn't assign it, but you can go do it if you want. Or maybe I didn't assign it, I don't think I did. Okay, so, my phone is ringing. I'm going to answer it. Rose, Miss Record. All right, so, in the same way that there are these coefficients of kinetic friction, static friction, there are also coefficients of kinetic friction. All right. So your force of kinetic friction is going to depend on that coefficient, and then again, it depends on the normal force. All right. So the equation we end up getting is this: the force of kinetic friction is just equal to the coefficient times the normal force. And again, it's constant, so you don't need to worry about your values. Good?
Yeah.
Any problems? All right, so here's that same example that we started out with. Remember I said we couldn't solve that last part? So it's the same example, but I added in a new piece of information. I gave you a coefficient of kinetic friction this time. All right? So it says make a free body diagram, describe what the box will do. So we already did A, we already did B, but C we couldn't finish before, but now we can. Okay? So our mass is 20 kilograms. All right, this time, our force of Roy is 130 newtons. We already found our maximum force of static friction. It was 127.4?
Yep.
And so we've now determined that that's not enough force to prevent the motion. Right? So nearly instantaneously, the object is going to begin moving. It goes from not moving to moving, right? And that means that we're going to switch over to kinetic friction. Okay? So, oops.
So we don't even factor in like the static friction at all when it starts moving.
Correct.
Okay.
Exactly correct. All right? So, force of kinetic friction, well, that's coefficient of kinetic friction times normal force. So for us, that's 0.4 times 196, and it gives you, I think it's 78.6 or 78.4. We got 78.4? I don't know why I'm still looking, because you guys clearly multiply those two numbers. 78.4 newtons. Right. All right, are we good?
Yeah.
All right, so that static that kinetic friction is now going to resist the motion. So, to determine the direction that kinetic friction is moving, or I'm sorry, to determine the direction that kinetic friction is acting, we need to decide what direction the box is moving. Fairly obvious in this case, but I want you to understand, the reason that kinetic friction is going this way isn't because Roy's pushing that way, it's because the box is going to move that way. So draw in a little arrow and indicate the velocity, and then now we can put in our force of kinetic friction now that we've processed the direction of motion. Cool? All right. So,
Did you say that kinetic friction is stagnant throughout the entire motion of the object?
the kinetic friction,
Yeah, sorry.
yes, that's correct. It doesn't change.
So you could calculate the net force on that to see how.
And that's exactly what we're going to do now, yeah. So yeah, once it starts moving, that kinetic friction isn't going to change until it stops or changes direction or your forces change and change your normal force or something. Okay? So my net force here is then going to be, well, it's just Roy's force plus my kinetic friction, right? So Roy's force is 130. My kinetic friction is negative 78.4. So the net force ends up being 51.6 newtons. All right, and so now we can find our accelerations. Force per mass, 51.6 newtons over, what was it, 20 kilograms?
Yeah.
And so you get 2.58 meters a second squared. Good? What else?
Are we gonna have problems where, like, say, like, he pushes and then he lets go and then
Yeah, totally. All right.
So that's accelerating to the right.
Correct.
So it's never gonna stop.
As long as Roy keeps pushing it, that's correct. It'll keep accelerating to the right faster, faster, faster.
What happens when Roy stops pushing it?
Let's figure it out.
Accelerate left.
What? I'd like-
No, let's do it. Still got a 20 kilogram box. You're still gonna have your same force of gravity. You're still gonna have your same normal force, right?
Yep.
It's sliding this way with some velocity.
Yep.
Because it's sliding that way, kinetic friction is gonna go this way with a force of negative 78.4 meters a second. Oh, no. Sorry, got ahead of myself. 78.4 newtons. So what's my net force? And then you can find your acceleration. And it's negative, right? Which is exactly what we assume, right? So what you just saw there is Roy pushes it, gets it going, and then friction stops. Good? Yeah, Alex?
So, force static friction in order to get, in order to get it moving. If you then were to, never mind, I think
You sure?
yeah. Like, you stop, all entirely stop pushing, and this force is like equal to the kinetic friction, it's still more than the static friction, so what's
Say that one. Say what's more than static?
So he pushes and it exceeds the
This is the 127, yeah.
but then he reduces it to exactly 78.4.
Yes. Then it goes with a constant velocity.
Okay.
And that was, I'm glad you asked that. That was going to be my next question. So, yeah, so Patrick said before, so it's going to keep accelerating. Yeah, that's exactly what's going to happen. So, but the issue is, in real life, when you're pushing something across the floor, you don't keep making it accelerate indefinitely, right? There's sort of that oomph to get it moving, right? Like if you've ever had to like a Matchbox cars rolled under the fridge, and you're like, oh, I gotta get that thing. You guys have kids that roll Matchbox cars under the fridge all the time, right? So you're like, oomph, right? There's that oomph to get it moving, but then once it's moving, it just keeps going, right? And so, yeah, that's the idea that once it's moving, you reduce your force and you don't need as much, right? Okay? Good? Like if you work out, which I clearly do daily, but when you first start lifting something, there's that like, right, to get it moving, but once the weight is up and moving, it's easier to keep it moving than it is to get it. Say that again? That's why it's weight forward. Yes. The coefficient, you mean? Yeah. All right, are we good? There might be a couple random examples that are contrary to that, but as far as I know, yes. All right, are we good? In fact, it would have to be, because if your kinetic was more, then it wouldn't have gotten started moving in the first place. So yes, the kinetic is at most equal to. Okay. All right. I think this is the last example we're going to do today. Yeah. Okay. So let's get through this. It's pretty quick. And then the homework is split up into 2 chunks. I think tomorrow I'm going to just give you guys time in class to work. Okay? Like literally, I don't think we have anything else to do. Day before Thanksgiving.
I'm pretty sure there's been someone who attached that every single day.
That's gonna be a sad day.
All right. All right, so it says Roy discovers that if he pushes the box horizontally with a force of 300 newtons, then the box will accelerate at 4.5 meters a second squared. Automatically, what should I do? Find the net force, right? If you know the acceleration, find the net force. I'm sorry, I thought that's what people said.
He said find the
Oh.
There it is. I saw half of this.
All right, leave him alone. You guys are brutal. All right, so your net force ends up being 135 newtons. That's weird. Roy's pushing with 300 newtons. Why is the net force only 135?
Kinetic.
Friction. What kind? Static or kinetic? Kinetic. How do we know it has to be kinetic? Because it's moving. We know it's moving because it's accelerating. So you can find your force of kinetic friction, right? What number plus 300 equals 135? Negative 165. And then you can find your coefficient, right? All right, so coefficient of kinetic friction, if you algebraify your equation, you get this.
So when you plug it into the kinetic friction equation, is it always absolute value with the force?
Yeah, that's correct, yeah. Yeah, I was processing that today, that if it wasn't, you'd have to put the little arrow, the vector arrow over it,
And you then have like a negative.
and then it would get it, yeah. Yeah, your coefficients are always going to be positive. Yes.
If you find the coefficient of static friction by like measuring how much force it takes to push the body, how was it measured? The coefficient of kinetic friction.
You would find the force needed to keep the velocity constant, right? Because then the applied force would equal the force of friction. Or not even. Apply a known force and find the acceleration and do what we just did here. Right? We applied a known force of 300 newtons, found the acceleration, and then worked backwards to find the force and find the coefficient. So it wouldn't even have to be constant velocity necessarily.
Yeah, I was just gonna ask about the lab.
It is actually, yes.
Wow.
I haven't completely written it, but that's where we're headed, yes. For the lab. All right, so